today we're going to go ahead and talk about the addition rule. The addition rule looks at the probability of an event A or B occurring. So, Wade, I think we should talk about one of the most challenging problems that we give our students, which can actually be solved using the addition rule.
Yeah, so it's incredibly tricky to think about this one. So we ask almost every student we teach, what is the probability of rolling two die and getting the red die being the 4 or the blue die being a 2?
So I'm going to go ahead and write this out. We know about the multiplication rule. The multiplication rule says what's the probability of getting a 4 on the red die and a blue on the 2 die. But now we're specifically looking at or. So what is the probability that we get a 4 on red or a 2 on blue? And like we said, this is a tricky problem, but actually students usually think it's pretty simple. What do they usually say?
So one really popular answer is to just say 1 out of 36. And 1 out of 36 is, how would you get that?
So 1 out of 36 would be basically confusing this with the multiplication rule, would be multiplying the probabilities together. So taking the chance of getting a 4 on the red is 1/6, and then multiplying that by the chance of getting a 2 on the blue, which is also 1/6. That would be the answer if this question said and. If I said, what's the probability of getting both of them? But it doesn't, it says or. So what's another common answer that we get?
So probably the second most popular answer is 1/3, or sometimes expressed as 2/6.
Right. So sometimes people know that or means to add. And actually the addition rule says that the probability of A or B, event A or B occurring, is equal to the probability of A plus the probability of B. And then, so students will actually just write that as their answer. But then we have to remember this key part of the addition rule, which says we have to subtract the probability of both. So in this case, the probability of A and B. So a lot of times students will forget this part, and it is super crucial. There's only certain cases where this probability is 0. Most of the time it's not. So are there any other answers that we get that are super common?
So I think the only other one is 11/36.
11/36, okay, which is actually the right answer. So we're going to talk about how to go ahead and do that. So if I was trying to figure this out, let's just say event A is getting a 4 on the red and event B is getting a 2 on the blue. So I would go ahead and say, what's the probability of getting a 4 on the red?
It's 1 out of 6.
1 out of 6.
Six-sided die.
Perfect. Plus, what's the probability of getting a 2 on the blue?
Another 6-sided die, so another 1/6.
1/6. And then the question is this probability non-zero? Can we get a 4 on the red and a 2 on the blue? Is this a non-zero probability?
So I have both of them happening right there.
Perfect. And we know that this is possible, right? We can get, we know from the multiplication rule that the probability of getting a 4 on the red and a 2 on the blue is just the two probabilities multiplied together like we said. So this is actually 1/6 times 1/6, or 1 out of 36. So we want to make sure that in our answer, we don't forget to subtract this 1 out of 36. And then, like Wade said, the next most common answer is 11 out of 36, which is the answer to this problem. I could, if I wanted to make this a little more clear, we could change these 1/6 to have the same denominator. We could do 6 out of 36 plus 6 out of 36 minus 1 out of 36. So I have a question. Why do we have to do this? Why can't we just say the multiplication rule, I didn't have to subtract anything? Why can't I just say the probability of A or B is the probability of A plus the probability of B?
Yeah, that's interesting. And I think this is one of the hardest things to kind of see, especially if you can't visualize it. Because when you're counting the probability of A, you're counting all of the possibilities of the 4 appearing. When you count the probability of B, you're counting all the possibilities of the blue 2 appearing. So in counting all the possibilities of the red 4 and the possibilities of the blue 2, you're actually counting the chance of getting a 4 and a 2 twice. So you're double counting.
Exactly. So I sometimes like to think with this example, it's a little complicated to kind of list out all the possibilities. But if I'm thinking about rolling a red die and a blue die, I could say, okay, the probability that I get a 4 on the red, just a 4 on the red, and I could get anything else on the blue. So I could list this out as I could get a 4 and a 1, I could get a 4 and a 2, I could get a 4 and a 3. Oops, I'm running out of room a little. I'll write smaller. 4 and a 4, 4 and a 5, and a 4 and a 6. So those are all the possibilities if I roll 2 dice that I get a 4 on the red one. Or we said we can get a 2 on the blue. So now I don't really care about the red one. I just care about the blue. So I could get a 1 and a 2. I could get a 2 and a 2. I could get a 3 and a 2, 4 and a 2, 5 and a 2, and 6 and a 2. And this is actually, these are where the 6 out of 36 possibilities come from. But you'll notice, actually, Wade, that I wrote one of them twice, right?
Yeah, you're exactly. Those 12 different possibilities, you're double counting one of them. I see 4 comma 2 twice.
Yeah. So that's why I have to subtract this 1 out of 36. That is the probability of getting a 4 and a 2 because I don't want to double count them. But this, again, is a complicated example because dice are it's a little tricky to think about what that means. But let's do another example, maybe with, let's do an example with cards.
Sure.
So what if I wanted to know, I'm going to go up here, what's the probability of getting a queen or a heart?
So as a computer scientist, I love formulas. So I would work this out entirely through a formula. So I would say this is a probability of a queen or means addition. So probability of a queen plus the probability of a heart minus the probability of both.
Exactly. So how many queens are in the stack?
So it's a full deck of 52 cards, so there should be 4 queens.
Yep, there should be 4 queens. So here's the queen of diamonds, and then here's the queen of hearts. Here's the one we want, the queen of clubs, and then we should have the queen of spades, which is right there. So the chance of getting a queen is 4 out of 52. Those are my only queens. And then hearts, how many hearts are there?
It should be 13 hearts.
There should be 13 hearts. I could pull out all the hearts if I wanted to, but there's 13 of them. And then the question I have to ask myself is, can we get both? So I'm going to go ahead and put these down. Here are all 13 hearts.
Well, you've got 12 in that pile. And then, yeah, the 13th one is right there.
Oh, yeah, you're right. These aren't all 13 hearts. Here's the 13th one. And so see how I'm counting the queen of hearts as a queen, and then I'm also counting it as a heart. So I have to subtract the probability of getting both, which would be the queen of hearts, and there's only one of them. So this minus 1 out of 52 is crucial, and I end up getting 16 out of 52 as this probability. Another just quick way you could think about this is if I said, say we had a group of people and I said, what's the probability that you're wearing jeans or have brown hair? At least in that case, you could be, we're both wearing jeans. I guess, do you have brown hair, Wade?
I consider myself to have brown hair.
Okay, it looks a little blonde. But we also both have brown hair, so we would be double counted. We would be counting as the probability of wearing jeans. We would also be counting as the probability of having brown hair, and we wouldn't want to count us twice, so we have to subtract that probability of both.